Okay. I love the tradition of introducing yourself not by what you do. I remember that actually being a very striking thing when I moved to America and how people go, "What's your name and what do you do?" And it always felt like a ranking thing for me. So when I came here, I was like, I knew it felt wrong. And they were telling the story. So I decided to add a little bit of, I think it's called Pepeja. I added uh, some images to tell you about my mountain. I come from Brazil. I was born in Rio de Janeiro. My mountain is Pão de Açúcar, which means sugar loaf mountain. There's a cable car that goes from one peak to the next. And if you ever get the chance to take that cable car, you'll see the entire bay of Guanabara. But I know, context. And you can see the entirety of Rio, and you can also see the Christ statue on the other side of this. And there's no real river per se there, but I grew up in the ocean. I mean, my entire life, once we moved from Brazil to Miami, I was still in the ocean. I've always loved salt water. Somehow I ended up in Oak Ridge National Lab, landlocked, and I've been living there for 14 years. It's killed my souls a little bit every year. And recently I moved back to Florida so that my child could attend college in Florida. But Guanabara Bay is the sort of picturesque place. I've been to these beaches all over the place. In fact, here's an early picture of me at the beach. My mom used to call me like a water baby. I've been swimming. I used to bodyboard. I used to do all sorts of things in the water. So, and fun fact, you might not know, is my people or tribe were called Cariocas. So when you come from Rio, there's a name for where you come from. And Disney actually created a character after Cariocas, Zé Carioca. So we have a Disney character named after who we are. So that's the fun fact there. Okay, so what's an HPC scientist doing at a startup? Good question. I don't know how I got here, but it sounded really cool at the time. So a little bit about my career trajectory. I started out in ag. I think I said that the first day that I was here. I have a background in physics and material science. And when I left grad school, the first job that I was offered, I took it. And I ended up working 3 years doing agricultural genomics. We were doing genetically assisted breeding. And we were essentially trying to breed out of the herd certain undesirable traits and also, try to select for desirable traits. Things that would, for example, undesirable traits would be things like susceptibility to pneumonia. We had a huge issue because before, when they were breeding animals solely based on phenotype, meant that a farmer would look and decide that, piggy A and piggy B should meet so they can have little baby piggies. But often because of economic, incentives, they would breed pigs that, for example, that grew fast, because if you can get a pig to market fast and you don't have to, feed the pig as much, you don't have the chance of the pig getting sick, which there are FDA rules about whether or not you can sell that pig. And that ended up causing a huge problem with something called scrotophornia. So the pigs grew too fast, the testes didn't descend, and they were very angry, not happy pigs, which caused an entire problem in the herd. So that was an interesting job. Our product was semen. So, you might not hear that word very often in HPC circles. And it was hilarious. People would call and be like, for semen, press 4. That was our product. I love telling the story because it's one of these things where you don't know where HPC is being used, right? We talked about earlier, what sorts of things are driving HPC usage. And I built them a cluster. As we started out, when I arrived, actually, I arrived, there was like 6 nodes. Hold on, 6. I can do this. There were 6 nodes. And the way that they would do it is they would use the SAS application, the software, the statistical software package, and it would double click on a little command, and it would like launch a command line thing from a Windows computer before Linux subsystem, and it would do top essentially on the node and figure out if somebody was running a job. And that was their idea of a cluster. And I was like, no, we can do so much better. So I built them a 20 node cluster. We had two, like gigantic nodes back then. The sorts of models they were running needed a half a terabyte of memory, which was unheard of. So when I moved to Oak Ridge, the idea that we were running a half a terabyte, and some people were like, no, you're lying. I was like, no, really, half a terabyte of memory is what we were running for our statistical models. And it was a fantastic first experience. I got a lot of freedom. To quote my mom, if you're a one-eyed mouse, then you're a king in a land of blind mice. And I was the one-eyed mouse. I knew just enough, and people would just sort of marvel at what I could do and improve. And one of the biggest projects I had was, and I was given a lot of leeway to do it once I improved their computing system, was to rebuild their database. So all of the genomic data would go into an Oracle database. And to get data out of that Oracle database, somebody in Germany, one of our employees in Germany, would start on a Saturday, morning, and download all of the genomic data that had been put in there through scripts and then whatnot that would come in through FTP dumps. So the genomic place would send data, it would go into an FTP folder. There was a script that would automatically run and dump the stuff into an Oracle database. And it was so complicated, it would grind us to a halt for about 2 days. So we couldn't run these things in the week because financial services needed the same Oracle database. Everything was very, very bad. And I found this startup that was building a columnar store. They ended up going under a few years later, but that columnar store still lives. It was called InfinityDB, and it still lives in MariaDB database today, which used to be MySQL. And so I had a lot of things to learn. Number one, the people that actually use it didn't trust that I could do this kind of work. They didn't trust that a physical scientist understood genomics. So to cut a very long story short, I started out in this realm that people didn't quite understand HPC, and then I go and work with a big iron at Oak Ridge. So after 3.5 years at Genus, I ended up working at Oak Ridge for about 6.5 years. And there I learned scale, right? So I went from 20 nodes to now let's scale this up and scale really big. And part of my work there was to teach people how to use the GPUs. And fun fact, I didn't know how to use GPUs, and I was in charge of training. So I said, well, let's learn together. And I started putting these events together where we would sit together because I didn't like the idea of a pulpit where I was teaching people how, sort of in theory, what things should work. And what we learned a lot was all of the constraints. I sat next to climate scientists. I sat next to physical scientists and material scientists. And I learned so much about their algorithms and the sort of constraints of why they couldn't just move to a GPU and what are the things that were preventing them from doing that. I also learned that a lot of code that I thought was kept up with was not. So we found lots of things, like the examples I like to use is we found a lot of x87 code that would have been there as legacy. We found a lot of things of loops that were just tailored just right to run on a blue gene and where cache, the cache sizes would fit exactly. And so those applications weren't kept up with. And what I learned is there's a lot of room for software improvement. So fast forward, I ended up at NVIDIA, did some more work in genomics. And then I had a friend from NVIDIA give me my name to the first startup that I was at was Next Silicon, which was quoted here earlier. And I signed that contract. 2 hours later, a friend of mine from NVIDIA calls me, Josh Patterson, our CEO, today. And he says, hey, I left NVIDIA. I'm doing a startup. Do you want to be one of our founders? And I was like, dude, I just signed. I can't do that now. And he's like, okay, well, can you be an advisor? And I said, I can do that. So I helped them with hiring, and I helped also with, telling people how to scale on HPC, et cetera, which is, despite us having amazing, smart, computer scientists, scaling is still a skill that is not, they're not coming out of computer science schools with that skill. A year goes into it, and he's like, I really need you. I really need you. I really need you. And my time at Next Silicon came to a close, and I was like, okay, I'm joining. So I joined about 2.5 years ago, and what we've been building as part of this software infrastructure, I've had a ton of experience just trying to get data to work. Just wrangling data is the most frustrating part of most people's lives. We want to get to the compute part, but we can't do that because just getting data to come to you and then looking at the data and doing anything with the data is extremely difficult. I worked on a project at Oak Ridge National Lab that had to do with VA data. Also, I worked one of the Cancer Moonshot projects, SEER data. It was supposed to be like gold standard data. We found dupes, we found, misspellings, we found all sorts of things in the gold standard data that hadn't really been dealt with. So I ended up here as like, all right, let's solve this problem. Let's, number one, solve the problem of connecting data. Number two, let's solve the problem of doing data analytics on accelerated systems. And then number three, let's solve the problem on how we talk about data or have systems talk to each other with data. So back to our founders, Josh, met him at NVIDIA, and Keith also was there. Darren had a ton of experience. He was one of the founders of the startup that ended up being bought, that was Siri, and also had a lot of experience at AWS and GE. And Rod, you might know him from some work that he did. So where these two folks met, the Rapids folks and the Blazing SQL folks met, was actually at a project at ORNL. We were Gordon Bell finalists, and the work that they did that was essentially massive amounts of data. They were doing all of these runs during COVID, and they were trying to just do these sort of ensemble runs, and that required doing a lot of creating test sets and validation sets and over and over searching through the data. And they were able to get a 52-fold speed up on that process, which up until then was sort of built by hand using pandas. And that's where these two folks met, and they were like, we can do this. We can solve, let's go at it together. Let's solve this problem. The problem we're trying to solve is pretty evident if you look at this graph. We've done a really good job of getting compute right, especially compute for AI, but the gap between data processing and compute for AI is increasing. So as we get, better and better GPU systems, how you do the actual data processing is still largely on CPU. In fact, the primary tool today that's used in a lot of scaling workflows is called Apache Spark. Apache Spark was built a long time ago. The back end of Apache Spark, or what the language is built in, is Scala, and it runs on a JVM. And this is a lot of inefficiencies. It's turtles all the way down, literally. A lot of inefficiency in the stack. So what we're trying to do is say, okay, well, let's put the data where it's going to be anyway for AI. Let's accelerate it. We have all of this experience and all these NVIDIANs. That's what we called ourselves at NVIDIA. We have all these NVIDIANs here. Let's accelerate data analytics. So for every 5x performance gain you get in an AI server, you are going to need a 10-fold increase speed on a CPU, and that's just not going to happen, right? So we have to move to the GPU. We have to move to accelerated systems. And you'll see some of the themes of what I've talked about in some of on the panels come up over and over. So to be clear, we're not building a database. What we're trying to build is a stack that's very flexible. We're trying to connect data together, and we're trying to accelerate how you do data. Part of the motivation is because so many of the hyperscalers have gone toward building their own systems, data systems, because they've outgrown things like Oracle databases, Postgres, MySQL, and so they've had to build their own. And if you might be old enough to remember what was happening during the NoSQL days, those are the same days that I was trying to solve this genomics problem. Those are these sort of newfangled, new database types for different kinds of data. Document data, image data, et cetera. And so they've had to go out on a limb and just kind of build their own stuff. And a lot of it has now come under the curation of the Apache umbrella. Okay. So the needs of data systems are growing. We see businesses need to go to the next level. So businesses cannot build their own data systems. They don't have the skills. They don't have the people. They're not going to hire the people. So somebody needs to build that for them and enterprise-wise. And they also have increasingly more complex requirements. I worked in consulting briefly after I left NVIDIA, and I worked a lot with pharmas during COVID. And in fact, I was working with one of the pharma companies that were trying to develop a vaccine for COVID, and pharmas are really interesting in their data. So all I was doing there was essentially setting up data lakes and data spaces for them to do their work for COVID. When you're a pharma company, you've bought all of these little baby pharmas along the way, or smaller farms along the way, and these databases never get harmonized and never get integrated. And so eventually workers leave, and then no one quite understands the schema of the database. And now you have all this data that you can utilize, and you can't really search through. Sometimes it may be even in systems that it's not, amenable for you to use. So it's really hard to do that. And the answer that the commercial world has come up with is saying, okay, well, let's put everything on a data lake, and then let's see if we can mine it. So we see data growth coming up. We see analytical complexity coming up. We see application complexity. Many more applications are trying to interface with different kinds of systems and data systems. And again, they're coming from different languages, and the APIs may or may not exist. And then we see problems with data movement, where you're having to move monolithic data sets and monolithic pieces of data. So we needed to build a data system that can scale with AI, scale to problems that are too big for Spark. We need to build things that are accelerated native. And in fact, I would even coin a different word. It needs to be polysilicon. So it needs to be essentially agnostic to the silicon that's running underneath. And that was a comment I made earlier in one of the panels. It also needs to evolve with enterprise needs. And that usually means being flexible enough to remove bits and pieces out of the system and, insert something else in that you might need to use. So the only buzzword I promise that I'm going to use is composable. In this sense, in this context, it actually means composable. We're really composing an entire data system stack based on your needs. So the first thing that we're going to solve is a user interface. User interface can be anything like, Jupyter, right? It could be a Jupyter notebook. It could be R. It could be C++. It could be Python. Anything that you're coming at, it can be SQL. Which flavor is SQL? That's another thing that a lot of people that don't work with databases understand, is that SQL is not a one, it's a many. Flavors and many types and dialects. Systems have many dialects of SQL. And so the user interface that we've picked to address this, and again, you can use whatever user interface you want, but we've chosen one to be a sort of a standard, but you can swap this in and out as you need. And what we've chosen is one called IBIS. So IBIS was created by Wes McKinney. Wes McKinney is the creator of Pandas, and also the creator of something else that I'll mention later called Apache Arrow. So this person's been thinking a long time about interfaces. And what's great about IBIS is IBIS compiles into whatever language of choice you might want. So you write Python, and then it generates whatever flavor of SQL, et cetera. So we have up to 20 engines out that we can speak to. We can speak directly to the engine. So that's the one that we've chosen. And it makes it so that you don't have to do any migrations. It makes it so much easier for you to do CI. It makes it so much easier for you to actually, keep up with the code base. The next one is the execution engine. Now, we're a commercial entity. We still got to make money somehow. And so what we built as part of the offering that we have, the entire stack is open source except for the GPU accelerated engine. So we even have an open source CPU accelerated engine, and we have some other engines that you can swap in that you've already purchased that it will speak to. But the one that we built is a GPU accelerated engine. And that one is called Theseus. So Theseus sits in the middle of this entire thing. So you have the interface here, all of the language that you're interfacing with. These are all your compute sort of workflows. You're doing AI, TensorFlow, PyTorch, Ray. That all talks to this. So Theseus will talk to that. And Theseus sits right next to you where your data is. It sits on the GPU. And our goal is to have Theseus run on all of these pieces of hardware. Right now, we have NVIDIA, but we can easily move to AMD if AMD can create a cuDF. So if anyone is working with AMD, please beg them for a cuDF version of their library. And then it can also connect directly from your data sources. So you've got data sources, interface, compute, and hardware. And the engine sits in the middle connecting it all. Let's see what it's not. It's not a framework. It's not a database. It's not a data lake. We're definitely trying to get away from things like walled gardens, and it's definitely not monolithic. So if you have had experience with databases, a database is a monolith. It has the engine there, it has a data store there, it even has the interface, but it's all in one. If you want to swap it out because, say, your data scientist uses R or uses Python, you can. You have to force that data scientist to use SQL. So what we're doing right now is something that allows that flexibility. And again, if you're going to run on the cloud, for example, you're running on a data lake, and we move back here. I'm running on Snowflake or Databricks. I have to depend on the silicon underneath that they have chosen to instantiate that on. And if I want to move to on-prem, and I have GPUs, for example, that's all I have in my data center, when I want to move to Azure and not necessarily pay for this, I have to do that, build that engine or find that engine on my own. So we're trying to give people flexibility to just by breaking apart these monoliths. The last part is the data storage. The data storage is the thing that I came here to talk about, and if we can agree on, it'll be great. So Apache Arrow is the platform that Wes McKinney started to build. It's actually about 10 years old now, I think. I think it was built around 2015, 2016, so it's almost 10 years old. And it's a framework to connect different kinds of systems. So right now what you have is if you want to move from Spark to, so let's say Pandas, you have to do a copy and connect. And then you have to what's called serialize the serialize. In other words, I have to make the data frame that comes out of Spark look like something that Pandas can ingest. And that's a lot of compute cycles, just moving data in a formation and then in a way, a layout that system can talk to. That's a lot of wasted cycles. And so what Wes thought is, what if we can come up with one type of layout? What if it was in memory so it could be fast? And what if all of these systems could talk to that one layout through either drivers or things like one of the things that we built was ADBC, which is the Arrow Database Connectivity. And we have even communications over network. So we have protocols that these systems can talk to one another. So that means that your data, once it leaves that system and travels to the next system, that system can ingest directly the data and make use of it directly. So inefficiencies continue today. We're trying to end this world of copy, convert, serialize. And here's what it looks like in HPC. So if you've ever had to work with NetCDF or HDF5, we've been doing this by hand our entire career. So we've been building composable systems, putting in libraries, and inserting them as we need, to go along the way. Hopefully they work in whatever system that you have in storage, or we have the libraries available, say in power systems, etc. We've already done the same thing, but what we need to agree on is that maybe some of these file systems that are often text-based, like, NetCDF is an array-based file store. You've got still so much data, and the government comes out as CSV. It's ridiculous. If I want to get data out of NASA, I have to go to a website, search for the data, and download a zip file from an FTP server so I can make use of it. I should be able to just log in and say, NASA, show me what you have. What data sources do you have? What sort of metadata do you have? And I still can't do that. So we have a lot of examples. I was running, before I changed out to director of HPC, I was running a DevRel team, and I had my DevRel team, my engineers, running all of these examples that just show, like, how can you get your data from CSV to Parquet, which are different kinds of formats that run underneath Arrow, one of the format. So why Apache Arrow? This is actually version of 1 in NetCDF. That's my joke for today. And so tabular data has been used for a long time. And we've been using it since, Babylonians. There are a couple of ways that you can use data, and you might see this as sort of the database kind of way, which is row-based. And for us scientists, especially as we transition to GPU, we know that columnar formats are better. So this is the same, sort of the old argument of array of structs versus structs of arrays, right? So in the data sort of at the very low, how you store systems, for workloads that are AI and HPC, the last thing you want to do is have it in a row-based. Because if I want to, for example, do an average of a temperature, I have to take my cursor, and this is the layout that it actually exists in disk. And I have to go 1, 2, 3, read, and I have to read each one of these things and literally count them, and then go to the next one and get all of it. So that means I'm doing an entire table scan when I want to just get 1 or maybe 2 or 3 values. This is why databases that are row-based end up being so slow. If I want to do the same thing for columnar-based, all I have to do is put the cursor right at the beginning of that column. And now it's a contiguous store, and I can just run through that contiguous space and do it and read it. And if I have, say, a really, really large data set, those contiguous spaces might be 2-4 gigabytes, and I can now make as many cores available, read the data in contiguous spaces, so I can make something very scalable. So I get things like compression, less data transfers, etc. And now if I have a column that I'm actually dealing with, that means that once it leaves my data store, whether this is a file system, just like a Parquet file, or a database or anything else, that means once it leaves this, it leaves it as a column. And if it leaves it as a column, now I can send it to compute, or I can send it to another data system. It travels ready for compute. When it lands on a GPU, it's ready for compute. When it lands in the next system, it's ready for you to do any sort of analytics you want to do. And if I put an engine next to this data store, then I can do that work next to the data store. So instead, I could be connecting to a NASA supercomputer or a NASA, data repository, and I can say, hey, NASA repository, give me the average, give me the sorts of data sets that have the average temperature that's X. Or give me these cities. Give me this zip code. And I can do that search there and not download the monoliths and do the data, wrangling myself. So the beauty of Arrow, which, by the way, is growing exponentially in terms of downloads, and all of the major data lakes now have connectivity to them. This is, I think, finally a place where HPC can let go of sort of old ways of doing store and meet enterprise and take advantage of all of these folks that are building these systems, because that means that we're going to get all the benefits of all of these developers along the way. And we can, we can easily mold ourselves into what AI data looks like, which looks a lot like scientific data. Here's some proof that we did a good job. This is a benchmark. It's hard to read. I apologize for I hate graphs that have tiny things, so I know I'm just waiting for our 2 people in marketing. We only have 2. The rest of the company is engineers to get to the point of where they have recreated this graph. But here's a Spark a workload. This is 100 nodes. The cluster cost per hour is about $200, and we've been able to reduce all of this to our max of about 10 nodes, and that was our 10 terabyte benchmark. We've also done a 100 terabyte benchmark, which I can't talk about yet, but we're increasing ever. So one of the things that I'm looking for is places that I can run above 1,000 GPUs. We've already run and scaled to 512 GPUs. So if you have access to 1,000 GPUs and you would like to share it with us for a brief, it's probably going to take 3 seconds. Please let me know because we would like to be able to do these scalability studies and show that we can do it. We also launched, so the reason why I'm here and I'm able to speak is because we finally launched, and that was the most exciting part of being in a startup. The previous startup is still not yet launched, and I couldn't talk about anything. And if you notice, I like to talk, and I like to be in front of people, and I like to build community. And I hated that I couldn't talk about things. So we finally launched. We launched with HPE. That's their Esmeralda, it's their data lake. And we have the engine actually running in there. We're still technically in beta mode. We're looking for people to test. And I am just begging for users, come to me. We're going to need a little bit of money just to make this kosher, and it's a business transaction. But we don't need a lot of money. All we need is to be able to make a business transaction, and let's try to get some scientific data and do this together and work on a partnership. I have a couple of folks that are in the lab systems that would like to go for a Gordon Bell again. In fact, our Theseus engine is kind of a grown-up version, way refactored version of Blazy SQL, and it's all written in C++, and it's written in the most amazing way. I mean, our engineers are fantastic. So we're doing this legit. We started from the bottom. We refactored everything. It's all in C++, CUDA. We can take this all the way. It already scales fantastically, and we're doing a great job. So I like to invite you to come and talk to us and do, let's work on SKA data, whatever you have, big data. I need big stuff. Our goal is to reach to the point where we can work on a petabyte directly. So takeaways, the stack is needed for many workflows. Everything that I've seen here, everybody talks about the compute part, but we never talk about the sorts of other things that go around. So in other words, the validation and then UQ, right? Uncertain quantification, the iterative process, all of those things slow us down. We're talking months often for that iterative process when the compute processing is so much faster. And this can speed up that iterative process tremendously. We can probably do easily anywhere between 10 and 20x. And so I'm asking folks to give us a chance to do it and to work with you. We launched Theseus. It's available through HPE. So if you happen to have an Esmeralda account already and you want to try it, great. If not, come talk to us, so we'll be able to, create a partnership. That's my role as the director of HPC, is trying to find these partnerships and, find these edge cases and break it. I want you to break it. I want you to say this is trash and give our engineers an opportunity to fix it. And the last thing is, remember, almost this entire stack is open source and open data standards. We're not trying to hide away from that. We're actually trying to build on a good chunk of, probably about a third of our engineers are just supporting open source development. And so we really believe in open source, and we've got Theseus as the engine and the core of it all that makes it possible. And that is it.
Thank you very much.